Hi, this is Dr. S and this is video 14 in my series on reaction rates for Year 13 A-Level Chemistry. In this video we'll look at how to use the Arrhenius equation to perform some calculations related to the rate constant. So just to remind ourselves that the Arrhenius equation looks like this: K equals A e to the power of EA over RT. So what we'll look at is how to actually calculate the rate constant using some given data. So let's say that I had a reaction that had a frequency factor or pre-exponential factor of 1.68 times 10 to the 10 dm3 moles to the minus 1 s to the minus 1. So that is a set factor for this reaction. It has an activation energy of 150 kilojoules per mole, and we perform this reaction at 250 degrees Celsius. And the question is, what is the rate constant? So let's look at how we would put these numbers in. Well, there are a couple of things to remember here. The units are not quite right at this point. If you remember from my last video, activation energy, we normally report in kilojoules per mole, but due to the fact we're using the gas constant, which is in joules per mole per Kelvin, we need to convert this to joules per mole. So that's 150,000 joules per mole. Temperature, again, because we're using the gas constant, that needs to be in Kelvin. So 250 degrees C becomes 523 Kelvin. Remember, we add 273 to turn from Celsius to Kelvin. Then if we put the numbers into our equation, we should see that K is equal to 1.68 times 10 to the 10 multiplied by E, remember that's a number, raised to the power of minus 150,000 over 8.314 times by 523. Remember, that's a power, so when you put it in your calculator, you often see there's an E to the X button. So E is the number and X is the power. If you then run that through your calculator, then you should get an answer of 1.75 times 10 to the minus 5. Then it comes to the units. Well, in the previous video we said that the units of K are the same as the units of A. So dm3 mole to the minus 1 s to the minus 1. And that would be the value of the rate constant. Now let's look at how that would be different if we change something. So in the next example, we're going to keep A the same, we'll keep EA the same, and we're going to change T. So we're going to increase the temperature by 50 degrees. So let's say now that T is 300 degrees C. If you want to try and calculate this, pause the video and then come back when you're ready. Okay, so the calculation should broadly be the same in that it would be K equals 1.68 times 10 to the 10 multiplied by E to the power of minus 150,000 over 8.314 times by 573. I'll just separate that with a line. And if you run the numbers, that should then come out as an answer of 3.55 times 10 to the minus 4 dm 3 mole minus 1 s to the minus 1. So you can see that the rate constant has increased 10 to the minus 5, 10 to the minus 4, which we'd expect because higher temperature, so we'd expect a higher rate of reaction. A bigger number of a rate constant means a faster reaction. Now let's have a look at another example in which we add a catalyst. So in my orange example, we're going to change the activation energy. So we'll change it so the activation energy becomes 80 kilojoules per mole. Again, if you want to have a go, come back when you're ready. Okay, so for this one, I'm actually going to keep the temperature as 250. You might have calculated it with 300, but I'm going to calculate it with 250 because that's the one I've previously worked out. So we'd have K equals 1.68 times 10 to the 10. Pretty much exactly the same, but this time it's 80,000 rather than 150,000. 3, 1, 4, 5, 2, 3, so it's the same as the top one. And here I get an answer of 171.79 dm 3 mole to the minus 1 s to the minus 1. Now that's a huge difference from the first one. All we've done is added the catalyst, changed the activation energy from 150 kilojoules per mole to 80, and it's actually increased the rate of reaction by about 10 million times. Huge difference. So I hope you can now get your head around these calculations. In the next video, we're going to look at a different form of the Arrhenius equation and see how we can use that to determine the Arrhenius constant. I'll see you then.